systems of equations. We're going to use the elimination method to solve these as well. But this time the systems are not going to be set up perfectly for us to just start right into using elimination. We are going to have to use multiplication in order to be able to get one of the variables to have a pair of opposite coefficients. It does not matter which variable you choose to start with. You can choose to eliminate x first, or you can choose to eliminate y first. I don't know if you notice the first two systems that I have here as examples. The blue, the dark blue, and the purple are the exact same system of equations. What I'm going to do one time is eliminate the x and solve for y. And then the second time, I'll do it in the other direction. I'll eliminate the y and solve for x. So starting with this first system of equations, I notice that in the top equation there's a 2 in front of the x, and in the second equation there is a 1 in front of the x. If I want to solve this by eliminating the x variable, I need to get them to be opposite coefficients. So how do I get this 1 that's in front of the x right now to become a negative 2? The reason I want it to be a negative 2 is because it's opposite of the positive 2 in the first equation. Well, in order to change a 1 to a negative 2, and I can only manipulate these equations through multiplication or division, I'm going to have to multiply both equations by negative 2. If I, for example, say, well, I want to add negative 3x to this side of the equation, that'll turn it to a negative 2x. But then you also have to add negative 3x to the right side of the equation. That doesn't help you eliminate a variable. It just creates another problem. So I have not changed the first equation at all. It's still 2x plus 3y equals 7. But now the new second equation, which I'm going to write in green just so that you can see that it's different, is negative 2x. I have to multiply everything in this equation, this second equation. Everything has to get multiplied by a negative 2. If I don't, then I'm changing the value of part of the equation. So I need to be fair and multiply everything by that negative 2. To do that, I have to distribute. So negative 2 times 2 becomes negative 4y. And negative 2 times 11 becomes negative 22. Now I will add these two equations together. Remember, if you create a pair of opposite coefficients, then you can always add the equations. You never have to worry about subtracting. So I'm going to add 2 to negative 2, which produces 0. So I've eliminated the x just for the time being. I'm going to add a positive 3 to a negative 4. And when I add a positive 3 to a negative 4, I get negative 1y, or just negative y. And I'm going to add 7 to negative 22. Well, 7 plus negative 22 becomes negative 15. I don't want to know what negative y is, though. I want to know what positive y is. So to undo the negative, I'm going to divide both sides by a negative 1. That's going to turn negative y into positive y, and negative 15 into positive 15. So for this system, right now I know that the y value has to be 15. I want to find the x value that goes with it. At this point, and actually way back up here when we got to this step, we were doing the same exact thing that we've done in the last two steps, the last two methods, I should say. The last video was solving systems with elimination. And the one before that, I guess, was solving substitution. So at this point, we're exactly like we were with solving by elimination. The only thing different is that we had to multiply by a negative 2 instead of maybe just a negative 1. Okay, so now that I know what y is, I can go back to either one of these original two equations and solve for x. I'm going to go with the second equation, the one that's underlined in green, only because there's no number in front of the x. So that tells me that's going to make it one less step for solving here in just a bit. So I'm doing x plus 2 times y. We just found out that y is equal to 15 for this system. And the equation says that this is equal to 11. So 2 times 15 is 30. And if I subtract 30 from both sides, I find out that x is equal to 11 minus 30, or 11 plus negative 30 is negative 19. So the solution to this system is negative 1915. If you want to check your answer, you would take your x value and your y value, plug it into both equations. For the first equation, you should get a 7 on the left, and for the second equation, you should get an 11 on the left. Okay, now I'm going to move to the same system of equations. It's written in purple this time. And what I'm going to do different, you might wonder, why are you doing the same problem? Well, what if someone didn't even realize that, hey, these x's are going to be easy to eliminate, and they said, I don't like y, I'm just going to eliminate y. The nice thing about solving systems with multiplication to eliminate a variable is that you don't have to look for which one's going to be the easiest. You can pick whichever one you want. So let's say instead of getting rid of the x first, like I did the first time, I looked at these and said, I want to get rid of these y's. What is it going to take for me to create a pair of coefficients for the y that are opposites? Well, right now I have one that's a positive and one that's a, but they're both positives, I guess I should say. I'm sorry. So I know that I need to be opposites. One of these has to become negative. So it doesn't really matter if I multiply the first one or the second one by a negative. The only problem here is these two numbers, the 3 and the 2, they're not the same. The only number that I can get them to be the same through multiplication would be if I could change them both to 6's. 3 and 2 both go into 6. So if I can change these both to 6's through multiplication, then I'm going to have my opposite coefficients. So in order to change a 3 to a 6, I'd have to multiply by 2. In order to change a 2 to a 6, I'd have to multiply the bottom one by 3. It doesn't matter that one's being multiplied by a negative and one is not, because remember, in the end, your ultimate goal is to have a pair of coefficients that are opposites of each other. Same number, but different signs. So the top equation is everything's going to get multiplied by a negative 2. Negative 2 times 2 is negative 4x. Negative 2 times positive 3y is going to be a negative 6y. And negative 2 times positive 7 is going to be a negative 14. The second equation, everything's going to get multiplied by a 3. 3 times x is positive 3x. 3 times positive 2y is positive 6y. And 3 times 11 is 33. So now I can combine my like terms simply by adding the two equations together. A negative 4 plus 3 will end up with a negative 1x. Negative 6y plus 6y, those eliminate. They cancel each other out because they're opposite coefficients. And negative 14 added to 33 gives me 19. Now you might wonder, how come you got 19 for x when the first time you did it we got negative 19? Well, we're not quite done with x. We solved for opposite of x, negative x. We want to solve for positive x. So we'll divide both sides by a negative 1, leaving me x equal to negative 19. Now I want to substitute the negative 19 in for x to find out what the y value is. I'm going to go to the original second equation because there's nothing that x is being multiplied by there, and it'll save me a step in the long run. If you don't realize that, it's no big deal. You should still get the same answer, as your neighbor would if you plugged it into the first and your neighbor plugged it into the second. So now I have negative 19 in place of the x, plus 2y equals 11. I want to get y by itself, so I'm going to add 19 to both sides. I have 2 times y equals 30. And to find out what I can multiply by 2 to get 30, I'm just going to undo the multiplication and use division and find out that y is 15. So my solution is negative 19, 15. The same thing we got the first time we solved it, but just using a different first step. Okay, now onto the third system. This one, I just wanted you to have more examples. I also didn't make any one variable having a 1 in front, because sometimes that's a dead giveaway as to what you're going to do. Again, you can choose whichever variable you would like to eliminate. You can try to eliminate the y's, and get their coefficients to be opposite. Or you can choose to eliminate the x's and have their coefficient be opposites. I'm looking at the x's and I see that the first coefficient is a 4. The second coefficient is a -2. I could turn that -2 into a -4 very easily if all I did was multiply that second equation by a 2. Okay, if you chose to eliminate the y's, you would have to multiply both equations by a number. Probably the top one by 5 and the bottom one by 3. Lucky for us on this problem, both variables are already opposites. One's negative, one's positive, so we don't have to worry about that. Okay, so the first equation goes unchanged, 4x minus 3y equals -12. And the second equation, 2 times -2x is -4x. 2 times 5 is 10y. And 2 times 13 is 26. Now my next step, because I created opposites, I can simply add these together. -3 and 10, that's going to be 7y. 26 minus 12, or -12 plus 26, that's 14. Divide both sides by 7, and I get y equals 2. Now to find out the x that goes with that, because our solution to a system always comes in an ordered pair, I need to substitute the y into either equation. There isn't one up there that looks any easier than the other, so I'm just going to go with the first one. 4x minus 3 times y happens to be a 2, equals -12. 4x, -3 times 2, -6, or -6. And now I can add 6 to both sides. And I am left with -6. Divide both sides by 4. And I find out that x is equal to -3/2, or on Moodle you probably would have to be able to, you'd have to enter it as -1.5, and then the y value was a 2.